Welcome to Constellations, the podcast from Kratos, where industry leaders share their thoughts and experience on the future of space business, policy, and opportunity. If you like Constellations, please support us by giving a rating and review on iTunes. And don't forget to share this podcast online to help our community grow.
Welcome to Constellations, the podcast from Kratos. My name is John Gilroy, and I will be your moderator. Our guest today is Ralph Ewig. He's the CEO of Audacy Space, which was recently recognized by Via Satellite magazine as one of the top 10 hottest companies in satellite in 2018. Audacy Space was launched in 2015 by a team of Stanford graduates, a SpaceX veteran, and NASA award winners. Audacy is a space communications service provider, and their mission is to deliver anytime, highly operable connectivity to spacecraft and launch operators. Today, we're going to talk about three things: real-time connectivity, spectrum crunch, and commercial space telcos. Ralph, you just heard about real-time connectivity. I think it's an attribute that's missing for much of commercial spacecraft. Why is this so important?
Yeah, hey John, thanks for having me on the show. I'm really glad to be here. And as you said, real-time connectivity is something that's close to our hearts. I think this really hit home for me when I was at SpaceX. As you mentioned earlier, I'm that SpaceX veteran that was part of the founding team of the company. And there, I was responsible for flying Dragon to the International Space Station. And in doing so, we had access to a relay system that NASA had launched in the 1980s called TDRS or TDRS. And that allowed us to have real-time connectivity. And I saw the contrast between being able to do that and what everybody else does, which is using a network of ground stations, which gives you much more intermittent access. And I thought, this is brilliant. It makes life so much easier from a space operations perspective. And thought, okay, maybe we can expand on that capability and make it a commercial service. And that's really where Audacy came from.
And so what we see in the market today, access to space has improved, a lot more satellites in the next 5 years. It seems like it's a perfect storm for real-time connectivity, doesn't it?
Yeah, it's kind of surprising how few people realize that we still have this challenge. And I think it has something to do with what we're seeing on the ground, the terrestrial applications. We were so used to having all-time on connectivity on our mobile phones or Wi-Fi wherever you go. So then most people think, wait, this problem should have been solved already. I'm actually surprised to hear that for satellites, this is the case, that they cannot communicate to the ground at all times. But what's going on is there's been a lot of growth in low Earth orbiting satellites in the last couple of years, which is where really this explosion of commercial space is taking place. And when you're in a low orbit, you're going around the planet once every 90 minutes, which is very fast. And that means that the time window you have when you're overhead a ground station and have the ability to communicate can be as short as 10 minutes. So you end up with these intermittent intervals of where you have opportunities to communicate with your satellite and long stretches where you have no such opportunity. And it's been a real burden on both the industry and on the operators to work with those constraints.
So we know you got a PhD from Stanford, so some things are pretty easy for you and hard for the rest of us. So tell us, what are the challenges in putting together a system like this?
Actually, just to be fair, my PhD is actually from the University of Washington. That was where I got most of my engineering education. But then I did go back to Stanford recently to get a business degree since I wanted to figure out this pesky money thing before starting my own company. But yeah, talking about the challenges, it's a couple different things. You're dealing with items as basic as just pure physics or geometry, all the way to very complex technology problems. But on the fundamental side, it's physics, it's line of sight. If you look at the scale of an orbit or a track of an object going around the Earth versus the size of the Earth, in low Earth orbit, you're so close to the ground, you can't see across the horizon. It's a very thin layer between you and the Earth, really. So overcoming that geometry problem was the first challenge. So we have to we should put our satellites into a higher orbit where they can act essentially like cell phone towers on top of a hill and then service all of our clients, which move around below us. So figuring out that geometry problem was the first part of it. And then the next question that came up is related to regulations. The use of radio spectrum in space is highly regulated, and that's because spectrum is a natural resource. It is ultimately finite, and there are rules who can do what with it. And we also had to make sure that what we were planning on doing wouldn't interfere or cause any problems for all the people who are already in space, communicating, doing the various things that they do. And then the last part is really technical. Once you know where you want to be and you have permission to be there, how do you build such a system that can actually function and communicate between objects which are moving tens of thousands of miles an hour at very vast distances and make it all work for not just one or two clients, but hundreds or thousands of satellites simultaneously.
Now, when you try to look at this, is this primarily focused on LEO satellite constellations? Are there benefits also for MEO and GEO as well?
Yeah, so essentially this can benefit anything or any object that moves around in space, with the one exception of GEO satellites. So geostationary satellites or geosynchronous satellites, they're in a special orbit where their distance is such that their period around the Earth is synchronized with the Earth's rotation. So from the ground, they appear to be standing still in the sky. And because of that, it's fairly straightforward to communicate with them. You can just point your ground antenna at one location, and then you have this always-on connection, which is how much of the telecom world operates today. And that's really not what we're targeting as our customers. However, everything else, whether you're below that altitude or above that altitude, looks as if you're moving across the sky, as seen from the ground. And then those objects certainly can benefit from a solution like the one that we're putting in place. We actually like to tell our customers we provide a dial tone in space or connectivity no matter where you are, anywhere from launch pad all the way out to the distance of the moon.
Well, earlier you talked about TDRS and NASA. So when I look at your solution, is real-time connectivity equally important to both the government and enterprise markets?
Yeah, that's actually a good question. Initially, when we started looking at this as a business, this was the fourth time I tried a very early stage company in the space industry. And one of the things I had learned in my previous iterations was that for a very young company, it's not always a good idea to look at the government as your first primary customer, just because there's a lot of overhead associated with doing business with the government. So we focused very strongly on commercial applications initially, which was really things like Earth observation satellites in low orbit, and also launch vehicles. But then as we became more mature, we attracted more and more attention from government customers as well. And today we actually have a pretty good mix between both commercial applications and then civilian government, NASA, and also defense applications as well. But it really applies to any object that moves around in space, and they can all benefit from such a system.
Earlier I kind of mentioned this and kind of teased this topic, but the dramatic in the number of satellites this year and projected in the next 4 or 5 years, has this made access to real-time coverage even more important than when you started the company?
I think so. It's a fair point to say that. What you're seeing is that everything continues to shrink. What used to be a mission for a very large monolithic satellite is now being implemented with a much smaller satellite, but then many of them. And the additional consequence of that is that those smaller satellites tend to be in lower orbits, and they don't have as long a mission lifetime. So in the past, maybe you had an Earth imaging satellite that weighed, let's say, a half ton and could last 10 years on orbit. Nowadays, you'll have a swarm of much smaller satellites, which weigh maybe 20 kilograms. But you have 100 of those, and then each one of them will only last about 18 months on orbit. And when you see this rapid cycling of many, many smaller space objects, their ability to communicate to the ground is much more limited just because they're not as big and don't have as much power generation on board. So for them to have the benefit of a relay network like the one that we're building helps them to be much more efficient in carrying out their mission. So you can design your small satellite to do just the one thing, like taking images in a specific spectral band, let's say, without worrying too much of how much of that satellite do I need to dedicate to the task of communicating that data to ground after I capture it.
I have a background in software development. They talk about agile software development. But this seems like really the classic case for agile software development is that, hey, guess what? We're going to put this up. It's going to change, modify, pivot. Some satellites are going up, some are going down. It really is a very dynamic environment, isn't it?
It is, yeah, and I think it's been a fantastic benefit to the space industry. We used to see cycle times which were 5, 10, 15 years.
Right?
And now we have the ability to really put something together in a small scale in a matter of months, put it up in space in maybe a year's time, and learn from it and make it better. And I think that has really tremendously benefited the entire industry.
Earlier we mentioned spectrum. You talked about being a finite resource. And there's a special word normally associated with this. It's called spectral crunch. It means a lot of different things. So spectral crunch, what does it mean for my listeners here?
Yeah, that's an interesting topic, and something that maybe I didn't fully appreciate before starting to tackle this problem. But essentially, the radio spectrum, or the frequencies available within you can communicate using radio waves, is regulated because there is a finite range of them available. So there are treaties at international levels where different countries have agreed to allocate certain parts of the spectrum for specific applications. For example, there's a range of spectrum frequencies you can use for emergency services on the ground, and then other range you can use for mobile phones, and then also a range that can be used to communicate with objects in space. And the way this is set up, the framework, is essentially any new entrant who wants to start a new project has to prove that what they intend to do does not interfere with the guys who are already up there. And since this has been going on since the 1960s, the availability of spectrum has declined over time because all of it has been spoken for, essentially. Especially the component that was allocated to communicate from space to ground has been incredibly busy and heavily utilized. So now we have all these new little satellites coming into service, and all these guys would like to be able to communicate with their satellite. So they will then go to a regulation agency in the United States, that would be Federal Communications Commission, and say, look, I'm planning on flying this mission. I need about, let's say, megahertz of bandwidth, and I would like to have the allocation in this frequency band. And the commission will then turn around and say, like, that sounds great. Please show to us how you will avoid interference of all the other 50 or 60 people who are already using that band. And as these satellites are in low orbits, which move very rapidly, this can be very challenging. So that's what's referred to generally as the spectrum crunch. There's more and more demand. The available amount that's out there hasn't increased. If anything, it's decreasing because it's more and more heavily used. And that has been a barrier for continued growth of the industry.
You mentioned the radio spectrum and space to ground. You know, these regulations get kind of complex. I mean, you solved the riddle, but this is going to be a real challenge for a lot of companies just trying to understand the complex, regulations for the spectrum, won't they?
Yeah, the regulatory frameworks are complicated and they're time-consuming. Just to give you an example, there is an international governing body called the International Telecommunications Union, or ITU, and they meet at something called the World Radio Congress, and those meetings happen once every 4 years. So if you're a young company and you're used to thinking in timescales of weeks or months, waiting 4 years to get an answer on anything seems absolutely daunting. So we looked at this as well and thought, this is silly. If I buy a mobile phone, I don't need a license for that because AT&T or Verizon already got a license for me. Why can't the same thing work in space applications? So rather than each individual company going through this process and trying to deploy their own phone line, essentially, there should be an existing network which we can all share. And we approached the regulation commission in Washington, D.C. with this idea, and they were quite supportive of it. So the idea is that rather than each one of these new satellites using their own allocation to communicate from space to ground, we use something called inter-satellite links, which is the communication from one spacecraft to another, to consolidate a lot of this traffic and then only downlink it to the ground in a very few specific locations. And that makes coordination for the space-to-ground component much simpler because you don't have 100 satellites talking all over the sky. Only like 2 or 3 which go directly to ground. And then we used all of the inter-satellite spectrum, which was previously not very used. It has been allocated a long time ago, in the 1980s actually, but nobody really was making use of it. And we can leverage that to collect all the data together into those relay satellites, which are kind of like our cell phone towers on the hill, and then bring it down from there.
Now, Ralph, an engineer would call that an elegant solution, wouldn't they?
Yeah, we like to think so. I mean, ultimately, it was just finding the path of least resistance, looking for opportunities for something that could be leveraged, and making use of it in an effective way that not just helps ourselves, but it really helps space as a whole, because we want to see this activity expand as much as possible.
Now, Ralph, thousands of people from all over the world have listened to this podcast. Now, if you're listening to this and you're in Brazil or Japan or China, all you have to do is go to Google and type in Constellations Podcast, click on Kratos and sign up, and we'll put you on the email distribution for this podcast and hear all kinds of insights from guys like Ralph. So, Ralph, tell me more about this commercial space telco thing. I mean, it sounds like you're trying to be similar to Verizon, AT&T, and Comcast, or am I pushing this a little too much?
Yeah, in a way, we've said sort of cheek and tongue that Audacy is the first telco company for users who are in space rather than on the ground. And in a way, I guess that's true because our business is very similar. We provide connectivity to other people, except our customers aren't people on the ground. They're objects that fly around in space. So it's probably a fair analogy to call us that.
You know, we can drive around town here and you can see different towers and everything else. And I guess building a terrestrial network's got all kinds of challenges, but, you know, a lot more difficult to build these in space, aren't they?
Yeah, space is a unique environment, and it has both opportunities and challenges which are very unique to that environment. For example, we have much further distances to deal with, and we also have to deal with objects moving at very high speeds relative to each other. But then on the flip side, we don't have to worry about buildings being in the way or obstructions like mountains and valleys. So pros and cons depending on where you're working on.
Earlier in the interview, you talked about the shape of the Earth and line of sight. There's another concept in physics called latency. So how do you deal with this latency problem?
Yes, that's an excellent question. So fundamentally, again, going back to the basic laws of physics, there is this universal speed limit of the speed of light. No information can travel faster than the speed of light. And that applies to radio waves as well. So dealing with the long distances in space, there is a fundamental limit to how fast we can send data from one point to another, and then that introduces a delay, which people refer to as latency. So to give you an idea, for our network, the Audacy network, the signal travels from a low orbiting satellite to our relay satellite, which is in medium orbit, and then from there back down to the ground station. And that introduces a delay of about 250 milliseconds, about a quarter of a second, which doesn't sound like a lot, but it actually is enough to be annoying if you were trying to make a phone call with this kind of a system. So we're not really looking at real-time voice communications, but it's primarily a system for data use. With that, it is still a dramatic improvement over what you can do now, where you might take an image, you have to wait 45 to 90 minutes to get to a ground station, and then downlink it, and then you have access to your data. So we certainly improved from 90 minutes down to maybe a second or half a second. But that's about as close as you can get to real time, just given the basic limitations of physics.
I'm thinking about 90 minutes now. In that process, you could get lost packets, you could get disruption. This reduction really has the potential to reshape the way we communicate in space. I mean, there's no more 90-minute delay.
That is an interesting point. Yeah, there's a lot of technology that was developed around this challenge of I send a command to a satellite, I have to wait till it gets back to me, and then I get the result. And it's almost like there's a good analogy to software programming. When I was a PhD student, which was almost 18, 20 years ago now, my advisor used to make fun of me saying, you guys have it so easy now. You write some software code, you hit enter button, and then you get a result. And if it doesn't work, you make it better. In our days, we used to make punch cards, and those punch cards had to go to a lab, and I had to wait a week to get my results back. So we had to be very, very careful to make sure our code was correct, because it took us a week to cycle through and give it another try. And similar things that are happening with space communications. When I task a satellite to do something, I have to be extremely precise and very, very clear on what I wanted to do before I sent that command, because I will have to wait an hour and a half or two, potentially, until I see the result of that instruction. Whereas if you move to this real-time interaction, it becomes much simpler to have real-time interaction, just try something and see what it does. And we're actually excited about this because it opens up participation in space to a broader audience. I can picture a classroom of high school students literally just pulling up a browser window and pushing buttons on a satellite to an experiment and see what that does. And it's possible because you're no longer dealing with resources which cost billions of dollars and took many years to deploy, but they only cost a couple $1,000, and you were able to get them up there in a matter of months.
I don't want to beat this book to death, but Clayton Christensen wrote a book, The Innovator's Dilemma. We all know it. Talks about disruption. We know that. I don't want to toss this word around, too casually, but it would seem that a relay like this out in space can, here's the big word, disrupt, the industry. It could change things a whole lot, can't it?
It can, yeah. I mean, there's only anticipate that our presence, once we're up and running, will have an impact on the existing industry. That said, we don't want to be disruptive as in a negative or an impact in a form that destroys existing capabilities. In a way, very much like my mobile phone works here in California, it also works in Singapore or it works in New York. No matter where I am, I can just turn on my phone and it works. And that is the result of open standards, which the industry has worked out over the years, which allows to have this kind of interplay between different providers. And we see Audacy in terms of the space network in a very similar way. There are existing solutions in play and they work just fine. It just work only some of the time. So the idea is for us to fill in the gaps and then for our customers to, again, use those open standards to transmit their information over any of these networks. So you can roam between different providers fairly transparently, and it just works no matter where you are.
Oh, Ralph, I'm reading a book called Space Barons, and they talk about, all the adventures with the usual suspects, Elon Musk and Jeff Bezos and whatnot. But I'm just thinking from the perspective of someone trying to put something in space, your technology could have an implication on these people who are going to deploy to space, won't it?
Yeah, we like to think so. I mean, for me personally, I've been a space cadet all my life. I started with my career in aerospace and have been working in industry, doing things anywhere from dropping space capsules off the coast of California to building rocket engines in a desert to having the privilege of participating in flying Dragon to the International Space Station. And space is certainly something that's very close to my heart. And
you're going way beyond space cadet, by the way. You're way you're like an admiral.
Well, the reason we're really doing this is because, or the reason I'm doing this is because I want to see humanity move forward and expand its space activities. And for me, this might be that one little Lego block that we can contribute that enables others to do more and build upon that success.
Crystal ball time now, Ralph. You've been at the center of a lot of these innovations in the industry here. So where do you see this concept of commercial space telcos going in the next 5 to 10 years? Who will be the key players? Where's it going to end up in 5 to 10 years?
I think we're really moving towards a new ecosystem of open standards. There's been very isolated capabilities where you can go to one provider or another. And we saw this almost, again, in the terrestrial analog in the early days of the telephone system, where you could have hard lines in different locations and you get it from one of the baby doll companies and that's the only choice you have in your neighborhood. And I think what's happening now is we're looking towards a future where you have choices. And that's because there are open standards, which allows you to get to an ecosystem very similar to wireless phone service nowadays, where you have a number of different providers. You can roam between different networks, and pretty much no matter where you are in the world, you can pick up a signal and do what it is that you would like to do, with all the implications that come with that. So I do see the availability of information in real time, no matter where you are in space, to have almost as dramatic an impact as it did on the ground when the internet came to be and did the same thing for us for life on Earth.
The free market and open standards, wow, it's gonna be just pretty great in the next 5-10 years. Ralph, unfortunately here we are running out of time. I'd like to thank our guest, Ralph Ewig, CEO at Audacy. Thanks, Ralph.
It's been fantastic. Thank you so much for having me on the show.
Thanks for listening to Constellations, the podcast.